Good day, Grade 12s. I'm Taryn Roberts, and welcome to STEM in Action's Boost series. Today we'll be looking at Electrochemistry Part 2. Electrochemical cells are divided into two sections for your Grade 12 syllabus. It covers the galvanic cell and the electrolytic cell. In Part 1, we looked at the galvanic cell, and today in Part 2, we'll be looking at the electrolytic cell. We'll be looking at the redox reactions involved in electrolytic cells, and we'll also consider some of the applications used in industry. But first we have to look at some of the pre-knowledge that we need to understand electrolytic cells. So we'll look at redox reactions. So let's consider the reaction between sulfur and oxygen to form sulfur dioxide. If we consider oxygen gas, its oxidation state is 0. When it reacts with sulfur, its oxidation state decreases to -2. This decrease in oxidation number reminds us of the word reduce or decrease, and so this process is called reduction. There is a gaining of electrons. If we now look at the same reaction, but we consider sulfur in this case, sulfur's oxidation number is 0 because it's in a neutral state. Once it reacts with oxygen, it forms sulfur dioxide and its oxidation state increases to +4. We now have an increase in oxidation number, and this process is called oxidation, and this involves a loss in electrons. So basically, redox reactions always involve a transfer of electrons. Electrolytic cells, there are two definitions that you also need to know, and that is of electrolysis. Electrolysis is the chemical process in which electrical energy is converted to chemical energy. And we also make use of an electrolyte during electrolysis. The definition of an electrolyte, it is an aqueous solution which can conduct electricity. So we're looking at electrolytic cells, and a great way to look at that is to actually run a copper 2 chloride electrolytic cells here in the laboratory. So let's get started. I've got copper chloride salt, and in my weighing boat I've got the nice blue. You can see that nice blue color, and I spoke about it earlier, that blue color is because of the copper 2+ ions that will then obviously be present in solution. I'm just going to add some more salt. So there we go. Copper chloride ions, or copper chloride salt. We've got distilled water in our beaker over here. We're going to make our electrolyte, which would be a solution of copper chloride, and we're going to use a glass rod. So we've got our copper chloride and the copper 2+ ions giving us that beautiful blue color. And so we've got our electrolytes sorted. Popped into here, we've got our positive electrode and our negative electrode. We're placing them into the electrolyte, and that closes the circuit, and immediately I can see something happening in each of the pencils, and it's not the same thing. So if we look at our positive pencil, I see little bubbles forming, but I do not see bubbles forming on the negative pencil or on the negative electrode. There's a distinct difference. My positive electrode has got bubbles forming. I'm going to take it out of solution, and I'm going to smell. Something smells, it smells quite strong, but the smell hasn't evolved quite yet. And my negative electrode, from here I can see there's like an orangey, definitely not the same pencil or graphite color, but definitely an orangey smell. I'm going to see all those bubbles are being released from my positive pencil, and I'm going to use the waft method. So, and I can tell you, Grade 12s, you might not be in this venue, but this pencil smells very much like bleach, so it reminds me of laundry work, or it smells like a swimming pool. And that tells me somewhere along the line we formed chlorine gas. At our positive electrode, there are beautiful gas bubbles forming, and that's definitely not happening at our negative electrode. There we have the tip of the electrode with a different color. So I'm going to take it out so that it's not obscured by the blue, and let's come and have a look here on the white paper. So here we can see the tip of this pencil. I want to compare it to a pencil that was not part of this reaction. And if we look at the tip of this pencil, they are distinctly different. Okay. So I'm going to take the pencil that you would be using in the classroom, and I'm just going to do a little up and down pattern. That's what it looks like with a regular pencil. Let's go and see what happens with this pencil. It looks brown. So my question is it brown? Because if it's brown, it would write with a brown color. Let's go and see. Unfortunately, it did not write with a brown pencil. This pencil is still a graphite rod. However, since the top has been colored and it's now formed a brownish color, I know that this pencil has not turned into a brown pencil, but it has a brown coating on the edge. And that's important, grade 12s. This pencil, oftentimes in a test or exam, they ask you, what did you observe? And then I often get this response from learners in the lab, and they'll say, the pencil turned brown. No, 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 the pencil did not turn brown, because if it turned brown, it would write with a brown color. Like, for example, here's a brown Cokie, and it would write with a brown color over there. Okay, so if it turned brown, it would write with a brown color. This did indeed not happen. So the pencil did not turn brown, but what we do know is that a brown coating formed on the tip of the pencil. So let's see if we can rub that coating off. There we go. There we are. So you can see the coating on the tip of the pencil. That was just covered there, and that was because copper 2+ ions were being reduced to copper metal, and that copper metal then covered or coated the tip of the negative electrode in the cell. So the grade 12s, I hope you can see that this copper chloride electrolytic cell is definitely not scary. It's actually quite beautiful and quite interesting how we can take electrical energy and convert it to chemical energy. And in this case, the chemical energy is evident of the decomposition of copper chloride to copper metal, which we found as a coating on the negative electrode, and chlorine gas, which we smelt as a bleach or a swimming pool smell on our positive electrode. So let's have a look at the chemistry involved in this copper chloride electrolytic cell. If we consider the electrolysis of the copper 2 chloride cell, in this case, the electrolyte is that of copper chloride. There are copper 2+ ions in solution and chloride negative ions in solution. The electrode is a carbon rod. We could use pencils, the graphite pencils. So there we have our reduction half reaction, which always takes place at the cathode. There we've got copper 2+ ions that are being reduced, because reduction always takes place at the cathode. These copper 2+ ions are being reduced to copper metal, and so this cathode will actually gain in mass, and you'll actually have a copper coating forming on that electrode. The copper 2+ ion, since it is now being reduced, it is what we call the oxidizing agent. You'll remember that we covered most of these definitions in part 1. So let's consider the other half reaction. At our anode, oxidation takes place at the anode. The chloride ions, they lose electrons to form chlorine gas. And you'll be able to, if you go through the process, as you waft, you'll be able to smell that sharp chlorine smell. It smells very much like a swimming pool or bleach. There's a yellowish greenish gas, and that's the chlorine gas that gets released at this electrode. And the chloride ions, because it gets oxidized, it is called the reducing agent. In this electrolytic cell, we now do not have two half cells like we did in the galvanic cell. Both the oxidation and the reduction reactions take place in one beaker, in one vessel. It needs electricity, and that's why you'll see our little cell providing the energy that this cell requires, because we are using electrical energy and we are converting it to chemical energy. This chemical energy is basically a decomposition reaction where we decompose copper 2 chloride salt or solution into copper metal at the one electrode and chlorine gas at the other electrode. And all of this takes place in one vessel, one beaker, unlike galvanic where we had two half cells and a salt bridge connecting the two. And in this copper chloride, or in this electrolytic cell, we've got electrons flowing from the anode through the wire to the cathode. So the overall redox reaction for this electrolytic cell, the oxidation reaction is chloride ions being oxidized to chlorine gas. Our reduction half reaction is copper 2 ions being reduced to copper metal. And once we can have the same number of electrodes on the right-hand side of our reacts to form arrow as that of on the left-hand side of our arrow, we are then able to cancel these electrons out. Remember, if we cannot cancel them, we need to multiply by a common factor in order to get the number of electrons equal on the right and on the left of our reacts to form arrow. Once we cancel these out, we collect our terms on the left of the arrow and we collect our terms on the right of the arrow. So for a copper chloride electrolytic cell, the overall reaction is copper 2 plus ions in solution plus chloride ions in solution forms chlorine gas and copper metal. This is something that you must be able to know. We've covered it in part 1 for the galvanic cell, and you can compare this overall reaction for the electrolytic cell, which we're looking at today. As I said, this is a decomposition reaction, and if we were to increase the current through the cell, the reaction rate would increase. And so we would be forming copper metal much faster at the cathode and chlorine gas much faster at the anode. Over here I've got a table which beautifully compares the galvanic cell to the electrolytic cell. Remember, we covered the galvanic cell in part 1, and we can compare them to energy changes. It's very simple. Both of these cells involve two types of energies, electrical energy and chemical energy. For our galvanic cell, we do not have a power source, so we are taking chemical energy and converting it into electrical energy. Remember, we got the galvanometer deflecting, or we were able to get a voltmeter reading. For the electrolytic cell, which we are investigating today, we are taking electrical energy, so we do have a power source, a cell or a battery, and we are converting that to chemical energy, where we're decomposing copper chloride to copper metal and chlorine gas. If we look at the chemical reaction, for your galvanic cell, that is a spontaneous reaction. We do not need any input of energy. Whereas for this electrolytic cell, we need energy because it's non-spontaneous. Its E0 cell is less than 0, meaning that it's non-spontaneous, it requires energy, and the type of energy input is that of electrical energy. So what do we need to set these two cells up? It's quite important, because if you know the components of a galvanic and an electrolytic cell, you'd be able to identify it in an exam or even draw them. So for a galvanic cell, we need two half cells. That's why we had two beakers, one for oxidation and one for reduction. We need electrodes in each of those half cells. We need electrolytes in each of those half cells, because if we do not have electrolytes, we will not be able to get electrons flowing in the half cells, let alone passing through the external circuit. And then this would be connected via a salt bridge to complete the circuit. For the electrolytic cell, we just need one beaker. Our oxidation half reaction as well as our reduction half reaction all takes place in that one beaker. We do, however, need a power source. So this could be a cell, which means the reaction is going to take quite slow. And if we increase this number of cells or have a battery, we're actually going to get this reaction happening quite fast. We need a power supply or a power source. And we also need both electrodes, the cathode electrode and the anode electrode, in one electrolyte in one beaker. The cathode and the anode, remember, do not learn cathode and anode as positive or negative, because they are different for these two cells. What you can remember is that reduction always takes place at the cathode and oxidation always takes place at the anode. And this is the same for galvanic and for electrolytic. However, if you look at this table, you can look at the polarity of these electrodes. They are the opposite for galvanic cells and electrolytic cells. And then the applications, we use galvanic cells. All our batteries, Those are examples of galvanic cells, where we are taking chemical energy and converting it to electrical energy. And our electrolytic cells, they have major applications in industry, in electrolysis, electroplating, electrorefining, and we'll explore some of those now. So let's have a look at some of the applications of electrolytic cells in industry. So what is electroplating? This is a process in industry where we take an object, normally a cheaper object or made of a cheaper metal, and we coat it with something more expensive. So I always used to like to use this example. So say you're at the taxi rank and someone comes and wants to sell you this chunky gold jewelry, and they say it's like 20 rand. Your alarm bells need to go off, because chances are that's not real gold. It's a cheap metal, probably like a aluminium tin or just tin, and it's been coated with the gold. Okay, so that is an application of electroplating, where people can make money by taking a cheaper metal and coating it with a more expensive metal. And what do they use? Electrolysis or electrolytic cells. A rule to remember, it helps you in answering these types of questions in your exams, is that the anode electrode is always the electrode which provides the metal for coating. The cathode is always the object that will be coated. And so a little rule of thumb that I've just come up with is that the result is always at the cathode. And so in this case, if your result is wanting to coat a metal, that object will be your cathode. So let's have a look at this in a quick little animation. So here we have a process of electroplating. How do we know that it's electroplating? Well, electroplating is an application of an electrolytic cell. So what do we need? We need one vessel, which we have over there. We need two electrodes. We happen to have a silver electrode, and we have a fork. We need an electrolyte. We have a silver nitrate electrolyte, our aqueous solution. And of course, we need electrical input or a power source. So we've got a selection of cells over there. And this electrical energy will be converted into chemical energy through electroplating over here. So in this case, what are we plating? We're taking a fork, and I can assure you it's very expensive to have silver forks, pure silver forks. So we normally take a cheaper metal and we coat it with silver. So let's have a look how that happens. What do we want? In this case, our result is we're wanting a fork or an object to be plated with silver. That is our result. So automatically, this fork here becomes our cathode. All right? And what do we know? What happens at the cathode? Reduction. Over here, we need a metal that we need for coating. And we are going to be coating the fork with silver, so we need an electrode, which is silver. That electrode will be our anode over there. So the silver electrode, it undergoes oxidation, because oxidation always takes place at the anode, and it releases silver ions and electrons. The silver ions move across to the fork, it picks up the electrons, and those silver ions get reduced at the cathode, and that silver metal that forms the coating on this fork, our cathode, our object which we want coated. This process is an application of electrolysis, and in industry we call this electroplating. So this is just an example of what actually happens in electroplating. In this case, the object is a fork. It could be a pair of earrings, it could be a medal, it could be a trophy, it could be anything that we want to coat with a more expensive metal in industry. So let's consider another application of electrolytic cells in industry. I've mentioned it before, but let's look closer at electrorefining. If you listen to the word, you've got the word or the part electro, so we need electricity, and refining. It means we're going to take something that's impure, refine it to become pure. So we take in an impure metal from its ore using electricity and electrolysis to purify that metal. So if we look at that animation, let's see, is it an electrolytic cell? Well, let's check. We have a vessel, one beaker. Inside we've got two electrodes, check. Those electrodes are placed in an electrolyte, check. And of course, we need a power source. We've got a cell over there. Remember, in English, we talk about one battery, a torch battery, but in science, we call that one torch battery a cell. And in science, a collection of cells is then called a battery. So that's stuff you learned in grade 9 and 10, just ringing that bell over there. Important here, we need a power source. Once we've got that circuit closed, you can see that the electrons are moving from the anode to the cathode. In this case, our anode is our impure metal, the ore that we want to purify. And the cathode is the result that we want to achieve. And what do we want to achieve through electrorefining? We want to achieve purifying a metal. So we want a result of a pure metal, a metal without impurities. So automatically, if we want pure metal out of this reaction, our electrode, which is our cathode, would in this case be the copper electrode. The impure metal, that would be the ore, and that's the copper with any other impurities that would make it of less value. We use electrolysis or electrorefining, and what happens is the impurities will form a sludge, and these copper 2+ ions will move from the anode. The copper metal will be oxidized to form copper 2+ ions and electrons. Those copper 2+ ions move from the anode. They move from the anode to the cathode. They pick up the electrons through reduction, and that copper 2+ ions gets reduced to copper metal, and that's our pure metal that we're finding over there. At the bottom here, we find a little gray, sludgy shadow. It's a very valuable, sludgy shadow. The impurities are sometimes of value. For example, those impurities could be silver, platinum, gold, and that gets released from the impure metal, and we could actually use it because it's so valuable. And so in that vessel, we could then just pump out the sludge, and that sludge can be separated into pure silver, pure platinum, gold, and obviously we could use that in industry. So electrorefining has many applications, not just purifying an impure ore, but the byproducts of that also have some value. Another application of using electrolytic cells is in chlorine production. There are 3 cells that we'd like to consider, and the first one is the mercury cell. So over there, we've got the mercury cell, and we've got our main vessel over here. You'll see we've got a hanging anode, and of course at the anode we have oxidation that takes place. This hanging anode is suspended in our main vessel. At the bottom, or the layer in that main vessel, we have a mercury layer or a mercury floor. That forms our cathode, where reduction will occur. So let's see how this mercury cell allows us to get chlorine and sodium hydroxide. So we use a very, very saturated or concentrated solution of sodium chloride, and in industry it's called brine. So the brine, there we have it, sodium chloride is pumped into this main vessel. And there's our mercury layer, and there's our anode. The sodium chloride obviously dissociates into sodium plus ions and chloride ions. And we need to know what happens to each of those ions. Very easy. The chloride ions, they get oxidized at the anode, and chlorine gas is released. The sodium ions, they get reduced, or they react with the mercury and form a sodium-mercury amalgam. This then drops down into the secondary vessel, where they decompose into sodium and mercury. This reacts with the water that has been pumped into this vessel, and it forms sodium hydroxide and hydrogen gas that is released. So these are 2 brilliant products. By using the mercury electrolytic cell, we can form chlorine gas and sodium hydroxide. Please realize that this reaction requires energy. We need electrical energy to convert to chemical energy. Let's consider another application of electrolytic cells in the chlorine production or the chlorine production industry. The diaphragm cell. So here we have an anode compartment, we have a cathode compartment, and they are separated by a porous diaphragm. This porous diaphragm only allows cations to pass through. So we want to produce chlorine gas and sodium hydroxide in industry. What do we need? A salt. Our salt is a concentrated solution, the brine, and it enters our anode compartment. The salt dissociates into sodium plus ions and chloride negative ions. And as usual, in our anode compartment, there's our anode electrode. The chloride ions in solution, they undergo oxidation to form chlorine gas, which is released via that anode compartment. The sodium plus ions, those cations, because of their charge, are allowed through this porous diaphragm, not because of their size, but because of their charge. That porous diaphragm is ion selective. So the sodium ions go into the cathode compartment. There's our cathode electrode, and they react with pure water and form sodium hydroxide and hydrogen gas, and these are released in the cathode compartment. This diaphragm cell, again, because it's an electrolytic cell, requires a large amount of electrical energy. The third cell that is involved in producing chlorine gas and sodium hydroxide is that of the membrane cell. Now these cells look pretty familiar, but you'll notice that in all three of them, we're producing chlorine gas and sodium hydroxide, which we use in industry. And in all of them, you have a cathode and you have an anode. And most of the reactions at the cathode and at the anode are the same. So for your membrane cell, we again have an anode compartment with an anode electrode. We've got a cathode compartment with a cathode electrode, and those are divided or separated with a membrane, and that membrane also again only allows positive ions to pass through. So what happens? Our brine enters the anode compartment, the chloride ions become oxidized, and that chlorine gas that gets formed is released over there in our anode compartment. So we get a concentrated brine solution, and we have a more dilute sodium chloride solution exiting our anode compartment. Sodium ions, where do they go? They pass through the membrane because of their ion, and they react with hydroxide ions to form sodium hydroxide. Where did the hydroxide ions come from? Well, that pure water gets reduced to form hydrogen gas and hydroxide ions, and the hydrogen gas is released, and the hydroxide ions are now free to react with the sodium ions which have passed through the membrane to form again sodium hydroxide. They are our products which are very useful in industry. These processes, as much as they benefit industry, they also have disadvantages. And so when we produce chlorine gas together with sodium hydroxide, chlorate ions and chloride ions form, and they react with the sodium ions to form sodium chlorate, which is found in household bleach. To prevent this from happening, we use mercury cells, diaphragm cells, and membrane cells to produce these products separately from each other. However, these cells do, however, have their own disadvantages. So if we look at the mercury cell, a very obvious disadvantage of the mercury cell is that mercury is expensive. And as much as it is expensive, mercury is also toxic. And it reacts with brine to form mercury 2 chloride. Also, the mercury cell requires a large amount of energy. The diaphragm cell, sodium hydroxide is quite dilute and impure, which gets formed, and the chlorine often contains oxygen in its production. So these are just some of the disadvantages that are experienced in chlorine production or the chlorine industry. Another application of electrolytic cells is that of aluminium recovery. So aluminium is found in a bauxite or aluminium ore. These ores are not found in South Africa, and they actually get imported from Australia. Once we get the ore in South Africa, we need to extract the aluminium metal from that ore. And this is the process. And this process, again, uses electrolysis. So here we have a lovely diagram of aluminium recovery. Again, we need anodes and we need cathodes. So let's have a look. Aluminium can be extracted, and we've got the formula for bauxite over there, Al2O3, with the selection of waters of crystallization. This aluminium is melted, or the ore is melted in a substance called cryolite. And this cryolite actually decreases the melting point of the metal, and it also allows the metal to obviously melt so that we can extract the pure aluminium from it. From the ceiling, we have carbon anodes. There they are dangling. And of course, at the anodes, oxidation occurs. And your O2 minus ions and your fluoride ions, they get oxidized to form oxygen gas and fluorine gas. That's coming from the melted aluminium. And then we have a flaw here. This flaw is a lining, and that's our cathode lining. At that cathode lining, the aluminium 3+ ions are reduced to form pure aluminium metal. And this aluminium metal, in its molten state, sinks to the bottom and it can then just be tapped out for use in industry. So this aluminium recovery is of much value in South Africa and makes brilliant use of electrolytic cells. Unfortunately, this process has some disadvantages. Number one, it's very expensive, and it obviously needs a lot of energy, or large quantities of electrical energy. The carbon rods need to be replaced quite regularly, and in that process, carbon dioxide is produced. The process is endothermic, which means it requires heat to be taken into the system, hence the large amounts of electrical energy required. And then large landscapes are being absorbed because chemical plants are so massive for this aluminium recovery to take place. And of course, where we have a chemical plant, we then have the release of greenhouse carbon dioxide gas being released. We've got groundwater possibly getting contaminated by the red mud. And we've got fluorine lost from cryolite is poisonous. Okay, and then it's a factory, it's a plant, so there's often quite noise pollution which surrounds the plant. These are just some of the disadvantages that are involved in aluminium recovery. So let's have a look at the application of electrolytic cells in a test or an exam. In this case, it's in paper 2, November 2018, and we're looking at question 9. So let's have a look at question 9. The electrolytic cell below is set up to obtain pure copper, so the alarm bells should go off, from a piece of impure copper. So immediately I know it's electrolytic, and we're looking at electro-refining. So it's important to take an exam question and tell your brain whereabouts in my content or in the topic are we and what is being tested or examined on. So those hints tell you exactly where you need to focus in your notebook or in your understanding and access the tips and the knowledge that you've learned in the past. So we've got a power source, which we now know it's an electrolytic cell. We've got 2 electrodes, we've got an electrolyte, and let's go and see what questions they've asked. They say the impure copper contains other metals such as platinum, iron, cobalt, silver, and nickel. The cell potential of the power source is adjusted so that only copper is deposited on electrode B. So here we're going to get copper solid forming on electrode B. And it's important because it's only copper, which means it's pure copper. And from our learning, we know if pure copper is the result, we know that the result happens at the cathode. That's just accessing information that we know. Let's see how that's going to help us answer these questions. Question 9.1. Define an electrolytic cell. So this is quite easy. These are the definitions that you need to know. They are covered in your Boost Prep Pack in the section of exam guidelines, and we've looked at them during the series. So question 9.1. An electrolytic cell is a cell which converts, and we're looking at the energy changes here, which converts electrical energy to chemical energy. And we think back of that demonstration where we had the power source and the circuit completely closed. And once the circuit was closed, we had a chemical reaction take place where copper chloride was decomposed to copper metal and chlorine gas through the process of electrolysis. Question 9.2. Write down the formula, important, the formula. So not the name, not the symbol, the formula of a suitable electrolyte for the cell. So this is important, ladies and gentlemen, and we've covered it in part 1 and a little bit in part 2. Whenever we have electrodes, we need to look at the metal of those electrodes. And when we have those electrodes in an electrolyte, that electrolyte needs to be a salt of that metal. So in this case, we've got copper electrodes, and so we need a copper salt. You only need the formula of 1. I'm going to give you 3 to choose from. So it could be copper nitrate. It could be copper sulfate. And a nice easy one that we used in our demo, copper chloride. In each case, the copper ion is a copper 2+. This is just add on. Copper 2+ ions in solution. There it's 2+, 2+, 2+. And it's that 2+ that gives the solution a blue color. All right? We can move on to question 9.3. Which electrode, A or B, is the cathode? And if we actually look at the question paper, the answer is there, because that's all the little learning, the tips that we discovered and we worked through during the series in part 2 right now. And we can confidently say electrode B is where our pure copper was formed, and the result is at the cathode. And so we know that cathode or electrode B is our cathode. Ladies and gentlemen, please note, during these episodes or segments, we look at the definitions, we look at the theory, but we also give you tips and associations to recall this information. You cannot go and write result at the cathode in your answer for an exam. That's not a standard answer, but result at the cathode is a tip or a recall technique to allow you to remember that the cathode that has the pure metal, or the electrode that has the pure metal or is the pure metal, is your cathode. That result at cathode is a tip or recall technique. You cannot write that as a reason for your physics or your physical science answers over there. So we can just say cathode is B. And then 9.4, they say write down the relative half reaction that takes place at this electrode. So we know that cathode is electrode B, and we know that reduction always takes place at the cathode. And so we know that we can say reduction half reaction. So we can tell our examiners we know what we're talking about, and we are confident. So we've got copper 2+ ions in solution. They gain electrons through a process of reduction, and they form pure copper metal. So those are worth 3 marks. You would get a mark for identifying the electrode, and you would get a mark for your reduction and your overall, your product. And our last question, 9.4, they say sludge forms below one of the electrodes while the cell above is in operation. You remember in that little animation, we saw that little gray shadow? That's the sludge they're talking about. And they tell us what's in that sludge. They tell us that we've got platinum, iron, cobalt, silver, or nickel could be present in that sludge. We're not sure which ones, and we're going to go and use our techniques from part 1 and what we've learned today to decide which metals or metal is of value in that sludge. So let's go and see. So platinum, I'm just going to write platinum, iron, cobalt, silver, and nickel. I'm going to use my redox table or my standard reduction potentials, and I'm going to write the E0 values. of that. So let's go and find them. So there we are. And let's go and find them. Be patient with me. But actually, as patient as you are with me, you're going to take your own table 4A or table 4B, and you're going to go and find those metals. So we've got cobalt. Yeah, I found silver. So I can write silver there as positive 0.80 volts. Platinum. I've got nickel there. It's negative 0.27 volts. Cobalt's underneath it there from table 4A. Remember, if you're using table 4B, the position might be this different, but the E naught values would be the same. So cobalt is negative 0.28 volts. Iron, there we are. Negative 0.44 volts. And we just need to find platinum. Not down there. There it is. Yay. Positive 1.20 volts. And so we look at those values. Remember, all the reactions, forward reactions on this table are reduction half reactions. And so let me go and be reminded of what was the question. They say, look at the sludge and decide which of the metals, these ones over here, will be present in the sludge. Now, for those metals to be present in the sludge, they must be in its neutral state. So they must form platinum solid, iron solid, cobalt solid, etc., etc. If we look at these E naught values, all these E naught values, the only ones that are that will be favored as a reduction half reaction is platinum formation and silver formation. Why? Because those E naught values are positive, which means the forward reaction is a spontaneous reaction, which means those platinum ions and silver ions are strong oxidizing agents and will easily be reduced to form platinum metal and silver metal over there. So they say which of these metals will be present in the sludge, and we'll say platinum and silver will be present in the sludge. And that's that. That section, or question 9, gave us 8 marks in the exam, which was November 2018. Grade 12s, I really hope that you feel more confident in having learnt the theory, the definitions, the little recall tips, and I hope that you feel more confident in applying them and tackling exam questions. So this has brought us to the end of part 2 of electrochemistry in our Boost series presented by STEM in Action.